Hello students, this is Dr. A.S. Sayyed. I welcome you all for the course on matrix method of structural analysis. We are dealing with the unit number 4, stiffness matrix method for beams. There are two important approaches in this unit, that is structure approach and member approach of the analysis. Since few lectures we have already discussed structure approach of stiffness matrix method. Now today we will start member approach of stiffness matrix method for the analysis of continuous beams. Before starting the numerical example, it is important first to derive the stiffness matrix of one standard beam element which can be used in the member approach. We know that in the member approach we have to find out stiffness matrix of each member one by one, that is K1, K2, K3 depending on number of members, and then we have to assemble all member matrices together to find out global stiffness matrix and then reduce stiffness matrix by imposing the boundary condition. Already we have discussed this process in the unit number 2 where we have solved the problems of bar structure and truss structure. So similar approach of member approach is used in the beam also. So in this class we will derive first stiffness matrix of one standard beam element. So we know that the beam is having 2 degrees of freedom at each node without considering any support at a point. If you consider any point of the beam, because of transverse load, every point of the beam has 2 degrees of freedom. Okay, those 2 degrees of freedom are vertical translation, which is also called as vertical displacement, and second is rotation. Like this is vertical translation and rotation. Okay, so if you consider one standard beam element, this one, if you consider this beam element, at left end let it be A and right end is B. Length of this beam element let assume L. Flexural rigidity of this beam element let assume EI. So without considering any support at point A, there are two unknowns, kinematic unknowns. Vertical translation, which is represented by 1, or you can represent it by WA. WA represent vertical displacement at point A. Similarly, second kinematic unknown at A is a rotation, which is represented by 2 here. If you want, you can represent it by delta theta A. Similarly, at joint B, vertical translation is represented by 3, or you can write down WB, and rotation at B is represented by 4, that is theta B. So at each point or at each joint of the beam element, there are two kinematic unknowns. Those are written here. 1 is equal to translation at node A, 2 means rotation at node A, 3 is a translation at node B, and 4 is a rotation at node B. So total degrees of freedom in one beam element are 4, and therefore the size of stiffness matrix, standard stiffness matrix of one beam element will be 4 by 4. Okay. Now we know that how to derive the stiffness matrix. Stiffness matrix is derived by giving the unit displacements one by one. So these are the 4 kinematic unknowns. One by one, if you give the unit displacement like WA equal to 1 first figure, theta A equal to 1 second figure, WB equal to 1 third figure, and theta B equal to 1, that is a fourth figure. From 4 figures we can write down the 4 columns of the stiffness matrix. Okay, now one by one we will see the unit displacement figures. So first, if you give the unit translation at A, unit translation means unit vertical displacement at A, that is WA equal to 1. Okay, WA equal to 1, which is represented by 1 in the figure. So when you are giving the unit displacement at A, please note that your second end must be fixed. So joint B is fixed here, Now we have to give the unit displacement at A. We are always giving the unit displacement in positive direction. Positive means vertically upward. Positive means vertically upward. It means we have to give the unit displacement at joint A in vertically upward direction. So if you lift this joint A vertically upward by unity, and since A and B is fixed, it will deflect like this. Okay, this is the deflected shape. This is A dash. Now since beam element is horizontal and we are giving the vertical displacement, means perpendicular displacement to the beam element, after giving the displacement it will bend. The bending moment created due to vertical displacement is 6 EI by L square. Okay, moment required to give the displacement in perpendicular direction, it is 6 EI by L square. If you remember slope deflection method, we are considering this moment in the slope deflection, that is 6 EI delta by L square. Now since delta is a displacement, we are taking delta is equal to 1 here. So delta equal to 1, if you take, the moment required to give the displacement in perpendicular direction is 6 EI by L square. Same moment is at the other end. Moments are same in magnitude as well as nature at both ends of the beam element. So it is 6 EI by L square at second end also. Okay. Now we have to decide the nature of moment, whether it is clockwise or anti-clockwise. So if there is any confusion to decide the nature, it's very simple to decide the nature. You draw one arrow in the direction of displacement like this. Draw one arrow in the direction of displacement and bend that arrow outside the beam element like this. So this will be anti-clockwise moment. You will get the anti-clockwise moment as a nature. Okay, it is anti-clockwise at both ends. So anti-clockwise moment is required now if you give the displacement at A. Magnitude is 6 EI by L square. Now we need to find out the reactions also. There is no external load on this beam element. So reactions will be developed due to these two end moments only, 6 EI by L square. Now how to find out reactions due to moment? It's very simple. We have to add the moments. Reaction due to moment is equal to sum of moment. Okay, what is sum of moment? 6 EI by L square. So if you take EI by L square outside, 6 EI by L square plus 6 EI by L square. So if you take EI by L square outside, it is 6 plus 6. That is 12 EI by L square. This is sum of moment. 12 EI by L square. Okay. 12 EI by L square. So how to find out reaction due to moment? Sum of moment divided by span. Span is equal to L. So if you divide by span to this term, it will be 12 EI by L cube. This is magnitude of reaction at two ends of the beam. Sum of moment divided by span. 6 EI by L square plus 6 EI by L square, 12 EI by L square divided by L. The answer is 12 EI by L cube. Okay. Now this answer is positive. Why it is positive? Because these two moments are anti-clockwise. Anti-clockwise means positive. We are taking anti-clockwise direction as a positive and clockwise moment will take as a negative. These are our sign conventions. Okay. Now since two moments are anti-clockwise, summation of these two moments, that is 12 EI by L square, is also positive. So 12 EI by L cube answer is positive. Positive means it is anti-clockwise. So now to write down the reactions, reactions are always having opposite signs of the acting forces, means acting moment. So since it is anti-clockwise, reaction will be in the form of clockwise couple. Reactions will be in the form of clockwise couple. How to represent clockwise couple in the form of vertical forces? Vertical forces means left must be upward and right force, if you write down downward, this produce the clockwise moment. Okay, it means now this left upward force will be the reaction of A and right downward force will be the reaction at B. These are the final directions of reactions. Okay, left upward, right downward. What is magnitude of both the reactions? 12 EI by L cube. Okay, so this is first figure. This is first figure to calculate the forces, moments and reaction due to unit translation at A. Now similarly we have to draw the remaining forces. So just I will erase all this part to understand. So reaction left will be upward, reaction right will be downward. Okay, similar concept is used in the remaining three figures. You please remember it. This reaction is downward. Magnitude of both the reactions I will write common, that is 12 ER by L cube. Okay, now understand the meaning of these forces also. This is very important while writing the stiffness matrix. Now we have to write down what is stiffness means. Stiffness is action corresponding to the unit displacement, forces required to give the unit displacement. So our kinematic unknowns are vertical translation. First, vertical translation, corresponding action is vertical force at that point. So this vertical reaction, it is an action corresponding to WA. Vertical reaction is an action corresponding to WA, and this moment, since moment is an action corresponding to rotation, when you apply the moment, the point will rotate. So this 6 ER by L square is the action corresponding to rotation, that is theta A. Similarly, this downward reaction is corresponding to vertical displacement at B, that is vertical translation at B, and this moment 6 ER by L square is corresponding to rotation at B. So these are the four actions corresponding to four kinematic unknowns. Okay, so this figure will gives you the first column of stiffness matrix. Okay, now similarly second figure is unit rotation at A. Unit rotation at A. So we have to rotate joint A in anti-clockwise sense. Okay, so if you want to rotate the joint A in anti-clockwise sense, we have to apply moment in anti-clockwise sense at A. This is the moment applied at A to rotate joint A in anti-clockwise sense. Why we are rotating joint A in anti-clockwise sense? Because we have to apply unit rotation in positive direction. Positive rotation means anti-clockwise. Positive rotation means anti-clockwise, and if you want to rotate joint A in anti-clockwise sense, you have to apply moment in anti-clockwise sense. Okay, so moment required to rotate any joint by unit rotation is 4 ER by L. Moment required to rotate any joint by unit rotation is 4 ER by L at the point which you are rotating, and it is half of that 2 ER by L at the far end. So it is 2 ER by L at point B. Okay, these are the moments. If you want, you can draw the deflected shape because of unit rotation. Since we are rotating in anti-clockwise sense, it will deflect upward. Its deflected shape will be like this. Okay, this is second figure. Now we have to find out reaction due to moments using the same concept. Now sum of moment divided by span. What is sum of moment? 4 ER by L plus 2 ER by L. 4 ER by L at A and 2 ER by L at B. 4 ER by L plus 2 ER by L, sum of moment is 6 ER by L. 4 ER by L plus 2 ER by L, answer is 6 ER by L divided by L. What is the reaction? Again, sum of moment divided by span. 4 ER by L plus 2 ER by L, 6 ER by L divided by span L. The answer is 6 ER by L square. This is the reaction magnitude. Coming to the direction of reactions again, these two moments, sum of moment will be anti-clockwise because both the moments are anti-clockwise. So if sum of moment is anti-clockwise, reaction couple must be clockwise. Clockwise means left upward, right downward, using the previous figure. Okay, this is clockwise couple. This is second figure. From this figure you will get the second column of stiffness matrix. Okay, second column of stiffness matrix. So this vertical reaction is an action corresponding to WA again. This is the action corresponding to theta A, that is 4 ER by L. Downward reaction is action corresponding to WB, and this 2 ER by L is action corresponding to theta B. This is second unit displacement figure. Now similarly third unit displacement figure. Now we are coming to joint B. Okay, we are coming to joint B. Unit translation at B. Translation means vertical displacement. In which direction? Vertically upward, because upward direction is positive. Now since we are giving the unit displacement at B, A must be fixed. A joint must be fixed. So we are giving displacement at joint B. Okay. So vertical upward displacement means like this. This is B dash. So deflected shape of the given beam element is like this. This is deflected shape. Now what is the moment required to give the displacement in perpendicular direction? It is similar to the first figure, WA equal to 1. Okay, so moment is 6 EI by L square. 6 EI by L square moment is required to give the vertical displacement in perpendicular direction. Perpendicular means vertical direction because beam is horizontal. Now what is the moment nature? Draw one arrow in the direction of moment displacement vertically upward and bend that outside the beam. This is clockwise now. This is clockwise in nature. 6 EI by L square is the magnitude. Nature is clockwise means minus we have to use in the further calculation. So this moment is 6 EI by L square, same at two ends. Okay. Now we have to calculate the reactions because of these two moments. So reactions are similar to first figure. Sum of moment, that is 6 EI by L square plus 6 EI by L square, 12 EI by L square divided by span. The answer is 12 EI by L cube. Sum of moment divided by span. 6 EI by L square plus 6 EI by L square divided by span 12 EI by L cube. Now please understand, now these two moments are clockwise in nature. Clockwise means minus. So when you sum up the moment, it will be minus 6 EI by L square minus 6 EI by L square. Answer will be minus 12 EI by L square. So this answer will be minus. Okay, minus means clockwise. Minus means clockwise. So reaction couple must be anti-clockwise. Reaction couple must be anti-clockwise. So what is the anti-clockwise couple then? For anti-clockwise couple, left must be downward and right must be upward. This is your anti-clockwise couple. Why it is anti-clockwise? Left downward, right upward. Please understand again. These two moments acting at A and B are clockwise in nature, 6 EI by L square. Clockwise means minus. So sum of moment will come minus. Minus means clockwise. So reaction couple will be must be anti-clockwise, opposite nature. So anti-clockwise couple means left force must be downward, right force must be upward. Magnitude of these two is 12 EI by L cube. This is third figure. Okay, I will write the corresponding kinematic unknowns again. This downward reaction is corresponding to WA. This 6 EI by L square is corresponding to rotation at A. This upward reaction is corresponding to WB. And this 6 EI by L square again corresponding to theta B. Okay, this is third figure. Now come to the last figure, that is unit rotation at point B. Okay, so we have to rotate the joint by unit rotation in positive direction. Positive means anti-clockwise. Okay, to rotate the joint B, first joint A must be fixed. Now since we are rotating joint B in anti-clockwise sense, we have to apply the moment in anti-clockwise sense at joint B. Why it is anti-clockwise? Because we have to rotate the joint B in anti-clockwise. If you want, you can draw a deflected shape of this AB element. Anti-clockwise rotation at B means it will deflect like this, downward. Okay, this is deflected shape. Magnitude of, what is magnitude of this rotation? It is 4 EI by L. Because we are rotating joint B now. So it is 4 EI by L at joint B and 2 EI by L at joint A. Both the moments are in anti-clockwise sense, but magnitude at far end is half in this case. In displacement case, it is 6 EI by L square, same at two ends. So it is 4 EI by L at B now 2 EI by L at A. And now we have to find out the reactions because of this moment. Now both the moments are anti-clockwise, so sum of moment will be anti-clockwise. Anti-clockwise means plus. Sum of moment will be anti-clockwise. Okay, 2 EI by L plus 4 EI by L, 6 EI by L divided by span. The answer is 6 EI by L square. Okay, this is the reaction, 6 EI by L square. How it is 6 EI by L square? 4 EI by L plus 2 EI by L, 6 EI by L divided by span is a 6 EI by L square. Now since both the moments are anti-clockwise, the reaction couple will be clockwise. Clockwise means left upward and right downward. Okay, this is clockwise couple. Because both the moments are anti-clockwise, their summation will be anti-clockwise, means plus. If answer is plus, it means it is anti-clockwise. Reaction couple will be opposite to that, it is clockwise. Okay, finally I will write again the corresponding kinematic unknowns. This vertical reaction is corresponding to WA. This moment is corresponding to theta A. This downward reaction is corresponding to WB, and this moment is corresponding to theta B. Okay, so these are the four figures now we have to draw by giving the unit displacement one by one. Now from these four figures we have to write down final stiffness matrix of one beam element, and it will be of 4 by 4. The actions, if you understand carefully, left reaction is corresponding to WA, left moment is corresponding to theta A. Right reaction is corresponding to WB, and right moment is corresponding to theta B. Okay, so with this, if you consider now first column of stiffness matrix. Okay, so look at this. This is 1 means it is corresponding to WA. 2 means it is theta A. 3 means it is WB, and 4 means it is theta B. First two columns are corresponding to left end, that is A, and remaining two columns are corresponding to right end, that is B. Okay, WA, first kinematic unknown, corresponding displacement is reaction. Second unknown is theta A, corresponding action is moment at A. These two, this is reaction at A and this is moment at A. Now third, 3 represent vertical translation at B, corresponding action reaction at B, and fourth column represent rotation at B, corresponding action moment at B. So from 4 figures we have to collect the reaction at A, that will be first column. Reaction at A represent the first column. Okay, so reaction at A, look at this. This is first element. Yes, this is 12 ER by L cube upward, so positive. Okay, then this WA means 6 ER by L square, upward, positive. This is 12 ER by L cube downward, means minus. This 6 ER by L square upward means positive. So plus 12 ER by L cube first, plus 6 ER by L square second, minus 12 ER by L cube plus 6 ER by L square. These 4 reactions in 4 figures is the first column. Similarly, second column deals with the theta A, that is moment at A. So this is anti-clockwise 6 ER by L square means plus, anti-clockwise 4 ER by L, it is plus, 6 ER by L square clockwise means it is minus, and 2 ER by L anti-clockwise, it is plus. This is second column of stiffness matrix. Okay, now third column of stiffness matrix means reaction at the B point, corresponding to kinematic unknown WB or 3. So this is downward 12 ER by L cube means minus 12 ER by L cube. This is downward 6 ER by L square means minus 6 ER by L square. This is upward 12 ER by L cube means plus 12 ER by L cube, and this is downward means minus 6 ER by L square. So first downward is minus, then downward minus, then upward plus, and downward minus. Magnitude are 12 ER by L cube, 6 ER by L square, 12 ER by L cube, and 6 ER by L square. And the fourth column corresponding to rotation at B. So fourth column unknowns, fourth column actions are, in first figure it is 6 ER by L square anti-clockwise, so plus. This is 2 ER by L in second figure anti-clockwise, so plus. This is clockwise 6 ER by L square in third figure, clockwise means minus, and plus 4 ER by L anti-clockwise means plus 4 ER by L in the fourth figure. So in this sequence these elements are identified from the 4 figures, and now this is called as standard stiffness matrix of one beam element. Okay, now this K of one beam element you have to use to solve the problems of member approach. So same element is applied to all member, only what will be the change? According to the span of member, this L you have to substitute length of element and proper value of I. If I is different, this I you have to change. this 12 and E part 6 or 4, this part remains unchanged for all members. Okay, so this is the standard stiffness matrix of beam element. I hope all of you have understand the derivation, and this stiffness matrix will use in the numerical example. Okay, thank you very much.